大家好，我是国立清华大学电机系黄衍介。今天我们要介绍电磁波打在一个介电物质上头，它的反射与穿透的现象。So in the last lecture, we focused on discussion about the electromagnetic wave instant on conducting boundary, and now we're going to switch the topic to a wave instant on dielectric material. And you will be expecting that the wave could be partially transmitted or partially refracted. And this is the topic we're going to talk today. And the first session is going to show you a simple configuration where you have a wave instant on a dielectric boundary along the surface normal direction of the boundary. And for the second part, we're going to talk about impedance transformation because we could be dealing with multiple dielectric materials. And this part is going to be closely related to transmission line. And for the third part, the situation becomes a little bit more complicated where we send a wave at an angle with respect to the surface normal direction of the boundary. And for section 10.4, we're going to talk about quite important phenomenon when you send a wave at an angle with respect to the surface normal direction. Finally, we're going to have some review. So in this first part, we'll be focusing on normal instance of a wave on the boundary of dielectric materials. And think about this scenario. This is material 1 with some material property described by the intrinsic wave impedance. And there's a flat boundary right here. And after this the flat boundary along plus z direction, you have second material characterized by the wave impedance eta 2. And the material properties are buried into the formula of eta 1 and eta 2, which is equal to square root of mu over epsilon. And so when you write down the expressions or describe the behavior of the wave, always remember that the material properties for material 1 and material 2 are different. And imagine that you have a plane wave instant on this boundary, and the electric field is polarized along x direction. And the magnetic field is going to be polarized perpendicular to this plane, and the direction of the propagation is the normal to this boundary. Last time, I already told you that there are a few steps to approach such a problem. The first step is to write down all the field expressions for the field for the wave inside a problem. Inside this problem, you have instant wave, and then I'm going to show you the refracted wave and transmitted wave. So first step is to write down the field expression for the instant wave. For this example, you have instant electric field polarized along x direction with some amplitude. And this wave is propagating, so you write down this exponential minus j beta 1z. And this beta 1 is going to be related to the propagation constant inside this material 1. And from the plane wave formula, you can also quickly write down the corresponding magnetic field, which is the polarized along y direction. And there's a proportional constant, which is eta 1, the intrinsic wave impedance in material 1. And this the magnetic field also propagates along z direction. So you can see that this is a minus j beta 1z shown in this complex exponential. And you can spell out this propagation constant in the first material. And this the beta 1 is going to be equal to omega multiplying with the square root of mu 1 epsilon 1. If we deal with the non-magnetic material, then we can further convert this expression to this one. But in this expression, beta 1, which is the propagation constant in the first material, is equal to 2 pi over the wavelength in the first material. In a non-magnetic material, you can use the vacuum impermeability as the impermeability in this material. So with this conversion, then the square root of mu epsilon is only depend on the epsilon r, the relative permittivity. And usually we write down the square of the refractive index to be the relative permittivity. So with this conversion, you can reduce this 2 pi lambda 1 to be 2 pi over the vacuum wavelength. And this N1 is called refractive index of the material. This expression is particularly useful when you deal with optics problems, because in optics problem, we usually describe a material by using refractive index. So after you write down the expression for the electric field and magnetic field for the instant wave, then now you can continue to write the components for the refractive wave. At the same time, you can have the electric field and also magnetic field expressions. So you write down the refractive field expression like this. This is the electric field and this is a magnetic field, but the wave propagates in the backward direction. Therefore, you see that before this, the GA, there's a positive sign associated with it, whereas you see minus sign for the first expression here. And this wave, the refractive wave, also propagate in the first material. So you can see that the propagation constant is also beta 1 here and also here. So the third step is to write down the transmitted wave. And so the transmitted wave here is propagating on the plus z direction. So now you write down this propagation constant beta 2 in the second material, but there's a minus sign before this J, which tells you the wave propagates along plus z direction. So let me just quickly summarize what I have done on this page. Basically, we write down the field expressions for the wave propagating along the first material. And this is the instant wave, and this is the refractive wave, and this is the transmitted wave. And the instant wave and refractive wave are in the first material. So you can see that the propagation constant is beta 1. And for the transmitted wave, which propagate along plus z direction, you get beta 2 as the propagation constant. And this beta 2 is going to be equal to 2 pi over lambda 2, where lambda 2 is the wavelength in the second material. So with these three expressions, then we are in the position to do boundary conditions. With the boundary conditions, then we can answer the unknowns in terms of the known parameters. And for dielectric boundary, there's no surface current on the boundary. So we're going to use the boundary condition as tangential component of both electric field and magnetic field are continuous. So let's just equate the boundary conditions into these two expressions at z equal to 0, because we purposely set the boundary at z equal to 0. So with the help from the last page, then you write down these two equations, and then in these two equations, you have known parameter, which is the instant electric field, because you set the propagation of the instant wave in the forward direction, so you know the amplitude from your source. And what is unknown is the refracted field amplitude and also the transmitted field amplitude. So you have two equations with this unknown and also this unknown, two equations having two unknowns, then you can solve this equation. And so we'll be interested in knowing the amount of the reflection generated through this instant process. So you calculate the ratio of the refractive field versus the instant field, and the result is this expression. So the reflection coefficient is given by the eta 2 minus eta 1 over eta 2 plus eta 1. And remember that this eta is our intrinsic wave impedance in the second material for eta 2, and eta 1 is the intrinsic wave impedance in the first material. And at the same time, you can also solve for the transmission coefficient, which is defined to be the ratio of the transmitted field amplitude over the instant field amplitude, which is equal to 2 eta 2 over eta 2 plus eta 1. And we want to discuss this eta a little bit, because by definition, this intrinsic wave impedance is equal to the square root of the ratio of mu over epsilon. But quite often that we only deal with non-magnetic material. So this impermeability can be written into the vacuum impermeability. But usually a dielectric material will have some value for the relative permittivity. So we keep this epsilon r. And for optics, we often want to convert this epsilon r into refractive index. And the definition for the refractive index is equal to square root of this epsilon r. So given this expression, you can further convert your reflection coefficient and transmission coefficient into these two forms. And for example, if you want to have the zero reflection, then this expression tells you that the N1 has to be equal to N2, and the boundary just disappears. So it's reasonable that if you don't have any dielectric boundary, you don't have any reflection. And on this page, I want to show you energy conservation. Energy conservation tells you that the instant power has to be equal to the sum of the reflected power and also transmitted power. And this is sort of a common sense from this scattering configuration. And when we deal with power in electromagnetics, we need to use the Poynting vector. And if you take the real product of the half of the complex Poynting vector, then you'll be calculating the average power carried by the wave. So this is the intensity. So if you do a surface integration, then you'll be getting the power transmitted through some cross-sectional area. So with this calculation, you can get this formula, which is the absolute value, square of the absolute value of the electric field divided by 2 eta, and multiplying with some effective area in your calculation. And assume that in this scattering configuration, the area are the same for the instant reflected and also transmitted waves. So this means that if you just take this energy conservation expression, then you can write down this expression. So this is the instant intensity equal to the reflected intensity plus the transmitting intensity. With this, and also the from the definition of the reflection coefficient and also the transmission coefficient, then you can write down this expression, which is a consequence of the energy conservation. This tells you that if you know the reflection coefficient, for example here, then you will be able to deduce your transmission coefficient from this expression. And for optics, we often use the refractive index, and so you can convert this eta intrinsic wave impedance into refractive index if we just choose the non-magnetic material. So the eta is inversely proportional to the refractive index. So you can just switch the position of this eta 1 and eta 2 to create this expression with the N1 and N2 right here. Okay. And from the scattering configuration on the last page, you know that when you send a wave at normal instance, part of the energy will be transmitted, part of the energy will be reflected. So if you just focus your attention on the first region, there will be instant wave and also reflected wave. And this is going to give you a standing wave in the first material. So that's sum over the instant wave and reflected wave, and then you're going to have a standing wave in the first material. And this expression is the same as the expression when we talk about transmission line connected to a row, because part of the wave could be reflected in the transmission line. So if you still remember, I show you this drawing, and this is the standing wave pattern in the first material, or in the instant section of the transmission line. Basically, you're going to have a standing wave envelope like this, and the wave will be oscillating within this envelope. For different time, the wave amplitude will be different, and but the total amplitude of the standing wave will be confined within the standing wave envelope. And we define the standing wave ratio to be the maximum amplitude of the total electric field to the minimum total electric field given by this expression. And turn out that this expression for the standing wave ratio is exactly the same as that expression for transmission line. So this is sort of a cross connection to our discussion for transmission line. So in this session, let me try to summarize a little bit. 如果说我们有一个波朝向于这个介电物质打过去的话，那你可以预期有些波会反射过来那有些波会穿透过去。那在解这个问题的时候呢，有几个步骤，1、2、3、4等等，在上一个这个 lecture 里头我有介绍过。那你如果要把这个未知的这个变数，像反射波的场的强度或者是穿透波的场的强度算出来的话，那你要把这个边界条件放进来。对于介电物质来讲的话呢，它不是导体，所以它不会有表面电流或者是表面电荷，所以呢，它的切线方向的这个电场跟磁场在这个边界上头会是连续的。那利用这个边界条件，你可以算出这个反射的这个场强或者是穿透的场强。那 as a function of instant field 因为 instant field 的话是你知道的这个场强。那在这个讨论里头，我有特别提到这个 energy conservation， 也就是这个能量守恒。然后呢，把这个reflection coefficient 跟 transmission coefficient 把它连接在一块，那代表说你如果知道其中一个的话，你可以推导出另外一个出来。另外我们介绍到这个 standing wave ratio， 因为部分的反射的这个波在第一个介质里头的话，会形成一个驻波，因为有往前传的波，也有这个往后走的波。那这个不完全的反射的话呢，这个量是多少？我们就是用这个 standing wave ratio 来描述，也就是我们形成驻波的这个波包的时候呢，最强的点除以最弱的点这个值会是这么一个这个式子。那这个式子跟我们在介绍传输线的时候，这个式子是一模一样的。所以在这里你可以看到，就是传输线跟这个今天要讨论的这个题目呢，有很强烈的关系，而且很多的相似处。那等一下我们还会继续的这个介绍。谢谢。